we left at a place where we said what are the structural properties of a matching if it has to be popular, right. So we said that if it has to be popular, then every F post is matched to an applicant who treats it as treats it as a rank 1 post, and if M is popular, then every applicant is matched to either its FA or SA, and we argued that it cannot be matched to somebody strictly between F and S, else it cannot be popular. In a very similar spirit, you should argue that it cannot be matched to somebody who is strictly worse than its S of A. Otherwise, you should be able to come up with 2 promotions at the cost of 1 demotion to show that there is a more popular matching. So this is the flavor of the argument here. So is this the end of the discussion? I mean, does this immediately tell us an algorithm? So this tells us how it looks like. Can we immediately tell what is the algorithm to compute a popular matching? If you know so much about the structure of a popular matching, what is an algorithm that you will propose? Yeah. See, we have some people participating. It will be very nice if many of you participate. I understand that, yeah, you have, yeah, not everybody can answer at every point, but please attempt to participate so that it becomes a little more interactive. I know it is the end of the day, but. Okay, somebody from this, yeah, you people have been a little silent, so. First pose. So she suggests the following algorithm, or she says that look at the F pose, then add edges to that. That's what I will do. I'll be constructing a bipartite graph, which is a reduced graph. I will cancel out all the F pose which do not appear as rank 1, and then look for S pose, right, which are the second choice pose. Then she seems to suggest that look at those and then cancel them out further and look for third pose. Now, does this theorem allow us to do that? So, okay, so I will assume that you have proved that it cannot be below its S post, because that is also crucial to this. Suppose you believe this, because the argument is very similar, so let's skip it. But let's say that it has to be between F and S, then should you go beyond your S post? You can look for third post, that is not incorrect, but will a popular matching be able to match an applicant along its third post? Yeah, so since you suggested, what do you think? Sorry? Yeah, so second came, right? Yeah, so there is a second choice. In fact, maybe there is also a third choice. Let's say there are posts remaining after your S post. Should you consider them? Yeah, second statement, yeah, sorry. Yeah, we have assumed that it is completely proved. I have not proved this part that P cannot lie here, but assume that this is true. And it is not difficult to see, because if somebody is matched to its a post which is lower than its S of A, you promote it to its S of A. If its S of A is free, if its S of A is not free, then there is somebody who is matched to its S of A. That person cannot rank it as its first post, therefore it has its own first post, promote that person, and you get 2 promotions at the cost of 1 demotion. So therefore this statement is true, that is, and if a matching is popular, then it cannot match anybody to outside its F post or S post. So then should we look for third post? A third post is only going to be below the S post, right? So therefore if we use that edge, then that matching cannot be popular. So therefore there is no point in using third post. So therefore we should restrict ourselves to a graph where we will have the applicants, and we will now use some color coding. We will say that there are these red edges which are, for every applicant there is a red edge, it goes to some post, this post is its F post, and then there are also these blue edges which go to their S post. Every applicant has an S post. We do not know how the S, there may be several applicants who have the same S post, some applicants who have their unique last resort as their S post, but every applicant has a blue edge and a red edge incident on it. Once we have constructed this graph, what question should we ask? Yes, we have constructed this graph. We know that if M is popular, it must reside in this graph. But what matching should we ask for in this graph? So we did it manually for an example, right? You actually constructed a matching, and we did not, we would like to show that it is, we would like to prove that such a matching is popular, but what kind of matching did you construct? Not the exact matching, but what were the properties of the matching? Which this? But remember, okay, so what she is saying is she matched some applicant to its L of A. Is it allowed to match some applicant to its L of A? Yes or no? Yes, because L of A can be a S of A for somebody. Therefore, it's okay to match it to its L of A. As long as you match every F post, it is okay to match some applicants to their L of A, right? So now we will simply construct this graph and compute a maximum matching of this graph. So this graph we will call as the reduced graph G prime. So G is the original graph, G prime is a reduced graph which has only 2n edges, and we will just compute a maximum matching in G prime. Now the maximum matching may be I mean, we just subject it to a maximum matching algorithm. There are several matching algorithms which can compute a maximum matching, but they do not have any regard to what is an F post and what is an S post, because those algorithms just operate on the graph. Therefore, they will just compute a maximum matching. In particular, in our example, they may have computed a matching which matches A1 to L of A1 and A1 does not match A1 to P1, right? It's just a matching of size, the largest size. Therefore, it doesn't know that LA is something which is last resort and dummy and so on. We cannot tell that to that algorithm. So therefore, it will output a matching which is a maximum matching. Now we will look at the matching, one by one and ask, look at a post. If it is an F post, if it is not matched, there must be some applicant who would like to get matched to that post. Takes any arbitrary applicant in F of P and assign it to that. Change the matching locally and keep doing this. You are not changing the size of the matching. You are not changing, if an applicant was matched, it continues to remain matched. There are some posts which will change their status, right? But you will always have you can ensure by this property that every F post is matched to an A belonging to F of P, and every applicant is matched to F of A or S of A, right? So we can compute such a matching. but these are only the necessary conditions for a matching to be popular, right? Because we have said that if M is popular, then it must satisfy these conditions. We would like to also argue that if you compute a matching which satisfies these conditions, then it is popular, right? If we argue this, then we are done. Then we will be able to prove that that matching that you constructed is indeed a popular matching for that instance without manually verifying all other matchings and comparing the popularity. Is that fine? Okay. So, so what are the steps? We compute a maximum matching in G prime and then ensure that every F post is matched. This is not difficult because you just examine every F post. If it is matched, not do anything with it. If it is not matched, take an arbitrary applicant in its F of P and match it to that by removing its matched partner. So you can keep doing this and ensure that every F post is matched. How long does this take? This takes as much as time required to compute a maximum matching in a graph plus this time which is linear time in the size of the instance, because it takes order n time to look at the posts and do this post processing. So it takes time which is required to compute a maximum matching. If you have a graph G with n vertices and m edges, then a maximum matching can be computed in m square root of n time by a very well known algorithm which is called as Hopcroft-Karp. We will not go into that. So a maximum matching can be computed in this time. So what is the size of our instance? We have n vertices. How many edges do we have? We have only 2n edges. We don't have a very dense graph. So this n is actually 2n. In fact, it can be even refined because it's 2n1, where n1 is the number of applicants. N is the total number of vertices, but we'll live with this. And therefore, our algorithm runs in time which is order n square root n. Right? This is the running time of our algorithm. In fact, this can be improved to a linear time algorithm, but for now we will just say that there is a polynomial time algorithm, assuming we prove the sufficiency. That is, if a matching satisfies these conditions, it is also popular. Right? Okay. So we want to show the sufficiency, that is, if M satisfies the two conditions, I won't write them again, then M is popular. Okay, so suppose my algorithm outputs a matching M by doing those steps. That is, it computes a maximum matching in that reduced graph and it does a post processing of the post so that every F post is matched. I get a matching M, and suppose it is not, so it satisfies the two conditions, yet it is not popular, right? So if it is not popular, there must exist, so M is output by the algo and it satisfies the two conditions and satisfies two conditions. Yet M is not popular. So then there must exist an M prime which is more popular than M. Otherwise we cannot say that M is not popular. To say that some matching is not popular, there must exist some other matching which beats it in terms of the votes, right? So what do we know when we did this comparison of M versus M prime in terms of these applicants, right? A1, A2 up to AN, there were n applicants. What do we know when we constructed this voting table? If M prime is more popular than M? So the number of votes that M prime got is more than the number of votes that M got, right? That is why it is more popular than that. So in particular, there must exist an applicant AI who votes for M prime. If all applicants vote for M, there cannot be the case that the matching M prime wins. So this AI is some applicant which must have voted in the favor of M prime. So we ask, what did this matching M, the matching output by our algorithm which satisfies the conditions, where did it match AI? We do not know anything about M prime. M prime may look completely different from the conditions of the lemma, this statement, right? We do not know, we have no handle on M prime. So we look at this AI and ask, who is your, so we will call this matching the red, okay, red I have used, but so the green matching and this as the pink matching M prime, right? So there is a green, so should it be matched in the green matching? So AI should it be matched in the green matching? So go back and ask what were the conditions of this, that is every applicant is matched to either its FA or SA, right? Okay, so should it be matched? Yeah, green matching is M, which satisfies this condition. Should it be matched or not? Yeah, so you say yes, you seem to say no, right? Okay, so why do you say yes? Okay, so it seems to say that every applicant is matched either to its F of A or S of A. So therefore it must be matched. But why do you say no? Right, but I never said that it should not be a last resort, right? So it can be matched to a last resort. It may not be truly matched, but it is, at least in the dummy sense, it is matched. So it is matched, right? It may be matched to a last resort, but it is matched. So we have certainly a green edge. How that green edge looks like, we do not know. And it can be either F of A or S of A, because our matching always matches it to one of F of A or S of A. But what do we know about M prime? M prime also it is matched and it prefers M prime over M. That is, it prefers its pink partner over its green partner. Now, if its green partner was F of A, could it prefer its pink partner? Remember that the pink partner must be different from the green partner, otherwise there is no preference, it may not have voted at all. So can this be F of A, the green partner? No. Therefore, the only choice that we have is its S of A, right? So this is the green partner, which is S of A. We don't know what S of A is. It could be L of A, it could be a true post. Now what should we do? Okay, remember that we are not in the game now to show that there is a more popular matching, because M prime need not be popular. It may just be beating M. We do not claim anything about M prime. So we cannot play that trick. But what we can try to do is, if for every applicant AI that votes for M prime, just the way in the stable matchings we showed that there is another applicant AJ that votes for M, then these are unique applicants. For each AI I find another unique applicant that votes for M, then I am done, right? So I need to find some applicant who votes for M. So this is M. This is M prime of A. Yeah, so this is AI. Yeah, yeah, we want to do that. Yeah, we want to nullify the votes. We want to find one applicant who votes for M. Yes. Sorry, who? Mhm. Will vote for. Yeah, but who is that applicant? Right. Yeah, so let's ask where is f of AI? That's what you are saying, right? Okay, good. So there is some f of AI, right? Yeah, good. Huh. F of AI, let's call that some AJ, and this is a green edge actually, right? Is that correct? M of, so sorry, M of, uh, that is its M prime partner. We do not know what it is. Yeah. It is just better than S of A. Yeah, it need not be the first. We are not assuming M prime is popular. Yeah, but what can we say about, so let's look at the preference list of AI, right? So the AI has its own preference list. There is something which is, it could be F of AI, right? So why did I write AJ here? It's AI, right? M prime of AI, and this is also AI. So AI has a preference list and it has F of AI. We don't know what is M prime. This is S of AI, which is also its M of AI, right? It is its green partner. Okay. So whatever happens to this, whatever, wherever this M prime is, it is here, right? Before the, so it is somewhere in this range because it is better preferred than S of AI. So it could be F of AI or it could be anything better. Now what do we know about all these posts? I mean, this is the its own F post, but what about a post which is sitting here? It is an F post for somebody, right? What does this, what happens to a green edge incident on this? This M prime of AI is some post, which is some P. Can it be left unmatched in the green matching? Because the green matching satisfies the two conditions. Therefore, there is a green edge incident on it, right? And that green partner of it is matched along, yeah, sorry, the green is different. The green partner of that is matched, is a rank 1 vertex, right? So this AK treats it as a rank 1. Now this AK, it's matched to its rank 1 in the green this thing. It cannot be matched to a green, it cannot be matched to a rank 1 in the pink matching, just because its rank 1 post is gone to some other applicant, right? Therefore, this AK vertex must give its vote to M over M prime, right? So you are correct that we should try to find some applicant that is matched to its first post and it gives a vote, but it cannot be this, because these two people could be matched to the same, I mean they could be matched in M and M prime in the same way. But we know that M prime of AI, which is equal to P, is matched differently in M and M prime, and therefore this is a unique applicant AK which gives its vote for M versus M prime, and these two together compensate each other. Therefore, for every vote that M prime gains, you can just look at this path and get another applicant who must vote for M over M prime. And remember, this is a different, while it's a simple argument, it's a different argument from showing 2 promotions versus 1 demotion, right? Yeah, then the green matching cannot leave it unmatched. Yeah, so she's asking that can it be F of AI itself? It can be, and if there is no other applicant that treats it as a rank 1 post, then the green matching is not allowed to leave it unmatched. So therefore, it doesn't satisfy the conditions of the claim. Then we don't say anything about it, right? So therefore, now we know that this, if we output such a matching, then if the matching satisfies both the conditions of the theorem, then one, they were necessary, they are also sufficient. That is, if this is a matching that satisfies these conditions, then M is popular. So is this now the end of this thing, discussion on, we know a complete characterization, or is there something that is remaining and which bothers you? Have we left something incomplete? Yeah, the size is a concern. That is, we showed that there are matchings of different sizes and we can ask computing maximum cardinality popular matchings. That can be fairly easily done by saying that I would like to have least number of last resorts to be assigned to applicants. So that is one thing. Anything else that is remaining? What about this instance, the first instance that we saw? So what happens when we execute our algorithm on this? So we should also, our algorithm should also handle the case that it should be also able to say that the instance does not admit a popular matching, right? Because there are instances which do not admit a popular matching. So when will you say that the instance does not admit a popular matching? Yes. Yeah, maybe she's just answering and we'll come back to you. Yeah. A1 has P2, A1 has P1, P2, P3. This thing, you'll have to observe this, is it? Actually, you are right in some way, but how will you try to observe it in a large instance, and where will you try to observe it? I mean, this may be masked. For example, I can add some things in between so that this is not as apparent as it is here. So you are right in, First 3. Only first post. If you have only first post and this is not there, then the instance does admit a popular matching. In fact, if you add this, then the instance stops admitting a popular matching. So we should make use of the theorem that we have. So we have stated a theorem that M is popular if and only if it satisfies the two conditions. We wrote it in 2 parts because we said that there is a necessity and there is sufficiency. So then what will happen to our algorithm? So maybe we should try to execute the algorithm on this. So we just do what the algorithm tells us. Everybody adds edges to F posts. This is A1, A2, A3. This is P1. Now what are S posts for everybody? For everybody it is P2, right? So we add these edges, P2. Now we compute a maximum matching in this graph. Any maximum matching must match only 2 applicants and it cannot match a third applicant. Now you cannot introduce a last resort and say that this last resort is your S of A, because that is not true. For A3, L of A3, there is an L of A3 sitting here because we pre-process the instance, but L of A3 is not even coming into picture. So its S of A is indeed P2, but you do not have enough pose between F and S to get matched. And if in this reduced graph where everybody has 2 edges, if you cannot find enough pose, or if the matching that you find is not a matching that is applicant complete, that is it matches all the applicants, that is it has size less than the size of the applicants, then you will say that the instance does not admit a popular matching, right? So I will just modify this algorithm. So ensure that every F post is matched, and then if, in fact you can do this immediately after computing the maximum matching, is if M matches all applicants, then instance admits a popular matching. Else instance does not admit a popular matching. Doesn't admit a popular matching. I would like to repeat this in this setting where we had this instance where there are n applicants, there is P1, there is only a single post. What is S of A? S of A1 is what is S of A1? P2. There is no P2, right? There is only P1 in the instance. There is a last resort, right? So S of A1 is L of A1, that is the last resort. S of A2 is L of A2, and so on. So the reduced graph, the original graph has n edges, the reduced graph has 2n edges, because everybody adds this dummy edge which we had called a pink edge, and this is, and now you can find an applicant complete matching which matches any one of them to its F post and everybody else to its S post, which is actually a dummy post. So it actually leaves it unmatched, but that does not mean that that matching is not popular, because our characterization does say that every applicant must be matched to either its F post or its S post. So as long as you find for everybody either an F or an S, you are happy. Any questions about this? Yes, you will have n plus 1 posts. Yeah, so we are not saying that the posts should get matched. It is not a perfect matching like we talked about in the stable matching setting where you had n and n. Anything, any questions? Yes. This example, right? Yeah, so what I'm saying is, what does our algorithm tell us to do for this instance, right? So this instance, we will actually convert the instance and write it with the pre-processing, right? A1, A2, A3 up to AN. Everybody has its, this is given to us. P1 is given as its top choice. This is all the instance that is there. Now we did a pre-processing step, that is, we said that for everybody add L of AI, L of A, A3 here, L of AN, right? So everybody, we add a unique last resort post, and now we ask what is F of A. F of A for everybody is P1. What is S of A? For each AI, it is L of AI. Now you construct the reduced graph. The reduced graph has P1 for everybody, and then I think the green edges, or the red, whatever, the green edges, and then there are these pink edges which are the S post edges. They are all dummy edges actually, but our algorithm allows us to do that. Our characterization says it's perfectly fine. So add those and then compute a maximum matching. The maximum matching does match everybody, at least in that graph. And then when we look at it, we ask, okay, even if everybody was matched to its dummy, we will take some applicant and match it to its P1, because we cannot afford to leave P1 unmatched, and then call that matching as popular, because we have found an applicant complete matching. Contrast this with this instance where there is no popular matching because you do not have enough posts. While the original instance does have P3, but P3 doesn't come into picture, neither do LA1, LA2, LA3 come into picture. So what I want you to observe is that this addition of last resorts is not changing the answer from yes to no. It is really a convenience, that thing that we have done, so that S of A always exists. Right? Okay. Okay, so now we are going to turn our attention to, to this model again, where we say that applicants submit their preferences and there is a central authority that is going to look at the preferences and compute a popular matching and output that, right? Now again, these agents or applicants are strategic. They would like to see whether they can improve their position by changing their preferences. Is it possible? Is it not possible? To what extent is it possible? What information does it require for us to be able to manipulate, and so on. So these are our questions, right? So even before we ask these questions, because we have started looking at popular matchings just now and we have understood the characterization, let's look at a very small instance where there are just A1, A2, P1, P1, P2, P3. This is a very simple instance, and stare at this instance and tell me whether this instance admits a popular matching or not. Yes? Does it admit? No. You don't know. Okay, so so there is an algorithm that we have given, so you should apply that algorithm. So what does our algorithm say? We have to do a pre-processing where we add LA1, we add LA2, and then ask for what is F post. So F post is A1, A2, and proceed with that. So does it, then we have to ask for S post, construct a reduced graph. Yes? Does it, yeah? Does it admit? Yes or no? Yes. Okay. So A1, so I will construct the reduced graph also. A1 P1 is an edge, A2 P1 is also an edge, and so S, what are S pos? A1 P2 and A2 P3, right? So the graph indeed has all the edges, and now what is a possible popular matching? A1 P1 and A2 P3, and you can observe that the other matching, that is A2 P1 and A1 P2, is also a popular matching, right? So there are two popular matchings, we call them M1, M2 and A1 P1, A1 P2, sorry A2 P3 and A1 P2 and A2 P1. Both of them are popular because both of them satisfy the conditions of that theorem, and they indeed are popular matchings. So now if the central authority chooses an arbitrary matching, then A1, let's say that A1 is our favorite agent, or A1 is ourselves whom we want to manipulate, we are not guaranteed anything, because if the central authority chooses A1 P1, the M1 matching, then it gets its top choice. If not, it gets its second choice, right? So what kind of things would a manipulative agent want to do? So for now we will assume that the input instance that is generated by the preferences does admit a popular matching. So we will not deal with the case that it does not admit a popular matching. We will also assume that the agent that is going to cheat, or the applicant that is going to cheat, knows all other information, that is, he has access to the fact that the preferences of all other applicants, right? Under these assumptions, we will ask how he can do things, but what would he like to do? So he cannot change what the central authority behaves. The central authority has declared that it will choose an arbitrary popular matching. It has all the right to change its own preference list. So one simple thing that the agent A1 certainly would like to try is, suppose it does not even say P2 is there in the preference list, that is, it says only A1 is there in the preference list, sorry, P1 is there in the, so this is modified to A1 with P1, just P1, and the A2 will not change the preference list, right? A2 is a very honest person, and this LA is anyway a pre-processing that we have done, but this is what is the instance. How is this instance different from this instance? Sorry, yeah. So the applicants certainly like to get matched over remaining unmatched, but a central authority does not promise anything. So let us draw the graph for this instance again. So let us say what is this graph. So it is A1 P1. We should remember that the algorithm is going to do the same thing. It does not know whether it is true references misreported. So going ahead, it will add LA1, it will add LA2, right? Just like it did earlier. Now this remains to be f of A for both of them. What is S of A for A1? LA1. So it will add the algorithm will add this edge, the procedure, and then it will also add P3, right? This is what it will do. Now the central authority will have two choices again. There are two matchings which are possible. You could argue that, yeah, the central authority will choose a maximum cardinality matching, but as of now that can also be beaten. So we will assume that the central authority chooses any matching, right? So the central authority now has choices. N1 is equal to A1 P1 A2 P3 which was the first matching as usual, and N2 which is even worse, A1 nothing, that is it is unmatched, or L of A1 and A2 P1, right. So going from here to here, which is all what he has in his, he can change his preferences, nobody else's preferences he can touch. He is possibly going worse, right, because if the central authority chooses an arbitrary matching, then he is even worse than what he got in any of the matchings that he had gotten in this thing, right, in when he had submitted true preferences. So we will say that this instance is certainly not this change of preferences is not benefiting the applicant A1, right. So what would A1 want to do in such a case? Yeah, so even if there are lots of agents and if he puts their posts as his second, third and so on, those are not candidates for S of A. So he will, so his first post he cannot make it as, he cannot make it as his S of A. So if that post is as an F post for somebody else, it will continue to remain an F post, right? Okay. So, but how will he change his preference list is a next question. What would he want in that modified instance? So currently the instance has this characteristic that in some popular matching he gets his F post, in another popular matching he gets his S post, right? So now what would be a better situation for him? Sorry? A2 is somehow forced to P3, right? Or in other words, yeah, that is what she suggested. So actually we can try that. So we can have A3 and that is having some P4 as his first choice. So you want this P2 to be as a P4, right? Okay, so if I change this to be P4, how does it matter? Because P4 is not going to be S of A. But you are on the right lines. Somehow you should not get your S of A, right? You should have a valid post and you should not be able to get your S of A, right? So instead of thinking about cheating and so on, because even if we want to think about cheating and manipulation and changing the preferences, let's assume that there are two preferences. Let's try to construct an example where an applicant gets its F post in every popular matching. Then we will see how do you come to such a this thing from some by modifying your preferences. So let's construct an example where an applicant in every popular matching of that instance, it must get matched to its F of A, right. So we would like to construct the preferences of other so now we are giving ourselves all the leeway, that is we will allow ourselves to set up the preferences of everybody. The instance is completely in your hands. You construct the instance such that in that instance there is an applicant which always gets matched to its F of A. So this applicant, both A1 and A2 are applicants which sometimes gets matched to their F of A, sometimes to their S of A, right. Anyway, there are only two ranks, two different choices if the central authority is going to output a popular matching. So let's try to construct an instance where every popular matching matches it to its F of A. Remember, this is not very different from what was yesterday. If I asked you that every stable matching matches A1 to B1, then you will be able to construct it by just putting B1's first choice also as A1, and then every stable matching must match that pair. Now can you do this for an instance in which a popular matching is forced to do this? Is the question clear to everybody? Maybe I will write it clearly. and it is a right thought that you would want your S of A not to be possible for a match for you. This is the right thought, but the way you are implementing it is currently not fully correct. So you should try some other option. Yeah, and there is a trivial this thing where there is a unique okay, so if this is the instance that you have in your mind, that is A1 P1, and then P1 is nobody's F post, then that is not an interesting instance because it's a post which nobody is interested in. Then yes, you can have, but there are, of course, I should say this, that there are at least 2 applicants who treat that as an F post. Still you would want that that post to be always assigned to A1, and you have the freedom to choose the preferences of everybody, not only you now, because for let's understand whether this can happen. So that's what I'm saying. Currently, let's not think about changing and so on. We are just saying that is there any instance in which there are 2 applicants who want P1 as their first choice, but because of the way the preferences of the other people are, it is forced that A1 must be assigned to P1, right? First of all, is there such an instance? If there is such an instance, then we will ask, can we modify our preferences so that our instance mimics those properties and so on? Right? Right now, don't consider the question of cheating. While that is the main goal, right now let's allow ourselves to set up the preferences of everybody. Okay, so let's ask some simple questions. Can the S of A1 for that applicant, so our interest is this, right, that A1 and A2, there is at least one more applicant who shares that F post, otherwise there is nothing to do, right, otherwise you don't have anything. But there are at least 2 applicants, so the graph must look like this, that is A1 and A2 must be matched, must have an H to P1. It looks like this. Now, can A1's SA be L of A1? If it is, then you are allowing yourself to be matched along something else, right? Therefore, it better not be some free post which you are only asking for, and that seems not to be a good idea. So it should be a post which is also in high demand by somebody else, so that it is in demand by some other set of applicants, and they cannot spare that post for you, for that applicant A1, right? So let's make this as our S of A. We will want to, yeah, so we will want it to be utilized by somebody. So how should we make sure that it is taken by somebody else? That is, it is not available for, if it is somebody else's first choice, will it even be your S of A? No, right? So it cannot be somebody else's first choice, but it can be somebody else's second choice, right? So let's make it somebody else's second choice. If you again make it A2's second choice, then you and A2 can share it at some point, just like this happened. So let's make it A3's second choice. Okay, but what is A3's first choice? Because A3 will have a first choice. So therefore A3 has F of A3. But A3 should not get F of A3. Or if A3 gets F of A3, somebody else should be able to consume or utilize this post. So what should I do with F of A3? Okay, so as soon as you make it somebody's F of A, it cannot be S of A for somebody, right? So let's we don't have dearth of applicants. So let's make another applicant A4 who also treats it as its F of A4. They both can share that this thing, and this is also its S post, right. So this is its rank 1, this is its rank 2 or whatever, I mean I don't know, but not rank 1, and this is again its rank 1. Now what about S of A2? So I do have an option of putting S of A2 here, that is this P2. Should I put it? So if I make this as S of A2, is it okay? So then the instance is complete. Now I cannot add more edges, right? Because everybody has its F edge and everybody has its S edge. Does this instance admit a popular matching? So I hope everybody is with me. So these are rank 1 edges, that is A1. So I will write the preferences A1 P1, A2 P1, A3, this is some P3, A4 P4, A3 has P2 as its S post and A4 also has P2 as its S post. We have also fixed A1's S post as P2. We are debating whether we should fix the A2's S post as P2. Should we fix it? If we fix it, this instance does not even admit a popular, because there are 4 applicants and just 3 posts. So therefore, if I do this, there is nothing wrong, there is no popular matching. Then the central authority says, boss, this is not good. So therefore, I just don't do this. But if I let some other post or L of A2, then I am happy. I mean, this is P4. Then this instance does admit a popular matching, because there are enough posts now to be matched within the applicants. So I can in particular match A1 P1, A2 P4, A3 P2 and A4 whatever P3, right. If I do this, this satisfies whatever conditions I had, because I have set up the preferences like this. But I should also ask, is there a possibility that I can match A1 to P2? A1 also has another edge incident on it. Can I try to match A1 to P2? If I try to match A1 to P2, A2 can nicely go to P1, but what will I do with A3, A4? So they cannot be matched within, because there's only one post which is P3 for them and they cannot be matched. So therefore, in this instance, we have the property that A1 in every popular matching, it's not that there is a unique popular matching, there is a popular matching which we have drawn here, there is another popular matching which can switch A3 to P3 and A4 to P2, right. And if you do this, then you will get another popular matching, but that popular matching also matches A1 to P1, right. So it has given a nice S post, but it has cleverly put an S post which it can never get, and this it has, so suppose it knew all of this, then it could choose this P2, right. Right now we have done it the reverse way, we have engineered this instance to show that this can be done. So our question in general is that if I select an agent or applicant and I would like to know, can it always get a better, can it get something which is better than what it currently gets in the popular matchings of this true instance? Is it possible? It may or may not be possible. So we would like to answer this question, is it possible for that agent to cheat? Is the question clear? We will make this formal, what does it mean to be better in that instance and so on. Yes. Uh, so I didn't get, so this first instance, right? A. Correct. Remember that the preferences of everybody else are fixed. In fact, so once the preferences of everybody, just the first posts are fixed for everybody, then the candidates for S posts are already determined, because anybody who is not in this set is only a candidate for S post. It's not the other way, right? So this, I don't know if you are confused by this example. What I was trying to illustrate is that in this example, I have fixed that two people should share P1. Now I do have the full freedom to choose S of A1, right? But if I choose it to be a nice post which I can get always, which is either last resort or something, or some post whom nobody is interested in as my S of A, then I can always get that post, right? That the matching can always match me along that. But that is what I do not want to do, right? And one more point that I should have emphasized that I did not is the set of F posts. So we can also talk about something like a set F, which is the set of F posts for an instance. Once the instance is fixed, I can say what are F posts and what are S posts, right? So can there be a post which is F, which belongs to both the sets F and S? No, so these are disjoint sets. So as soon as you say that a post is an S post for somebody, it cannot be an F post for somebody, and vice versa, right? So this is just by the definition of what we did as F post and S post. Okay, so so let's again stare at this instance. So if for some reason my true preferences are like this, that is the A1 applicant has its true preferences as P1, P2, and the rest of the agents have these preferences, then there is no reason for that person to manipulate, because whatever the central authority does, there may be several popular matchings. No popular matching can match it along A1, P2, that is its S post, and it is always guaranteed a true, it is always guaranteed its F post. Therefore, there is no reason for it to manipulate, right? So keeping this in mind, what we will do first is, suppose there is this instance G and there is instance G, and assume that G admits a popular matching. So in G, all agents have their, applicants have their true preferences. With respect to this true preferences, let's divide the set A. The set A is the set of applicants into three groups. So we will call them as AF agents, AS agents, and AFS agents. So what does this mean? That in all popular matchings, the agents, the applicants belonging to this set AF, they always get matched to their first post. There are other applicants who, irrespective of what popular matching is chosen, they will always get matched to their S post. And you can also construct examples of that kind, because the way you did, you said that you could utilize your S post somewhere. You can also force that the F post is required at some other place, and you are always forced to be matched to your S post, right? So there can be applicants who belong to this set, which is AS, and then there are these applicants who sometimes get matched to their F post and sometimes gets matched to their S post, right? So we do not know how to make this partition as of now, but if our agent A1 belongs to AF, then there is nothing for that agent to do. That is, it can already say that whatever is true preferences is good for me, I don't want to manipulate, right? So suppose the agent, suppose we are able to compute these sets, we will be able to at least resolve this case, that is the agent or the applicant AF agent, right? So what we will do is, we will take a small detour and try to categorize agents like this, which will also help us develop some things which are required for doing this manipulation, right? Any questions till here? So we have not formalized what kind of manipulation is required, but we are just saying that given an instance in which all preferences are true preferences, we would like to distinguish between three types of applicants, one which is AF, one which is AS, and one which is AFS, and every applicant must lie in one of these three sets. And we want to just partition the set of applicants into this. So A is equal to this. And this is a disjoint partition, that I mean this is disjoint union, sorry, that is this is a partition of the set. Any questions still here? Okay, so I'll recall what we said yesterday about stable partners. So now we'll say similar things. So if I have the preference list of an applicant, there is P1, P2, P3 up to some Pk. So what I want somebody to do for me is just underline the posts that I can get in some popular matching, right? Can it happen that there are 4 posts which are underlined Pn, which I can get in different popular matchings of the instance? So what I am saying is that there is somebody who did all the hard work and said that I will for every applicant I will mark the post that applicant can get in some popular matching of the instance, right? So just to make this concrete, we will ask, so what are the underlined posts for P1 in this instance, A1 in this instance? P1 alone, because that is what was our goal. What are this for A2? Yes? Yeah. Yeah, P1 is it? P1 and P4. So now let's see, is there a popular matching that matches A2 to P1? P1, we actually constructed this instance so that P1 must be matched to A1, right? Therefore, you cannot underline this, right? So that the algorithm that does this cannot say that A2 can get matched to P1. What about A3? Sorry? P3? Okay, so P3, and what about P2? Yeah, behind you. Yeah, what is your answer? Should I underline P2 or not? Yes, because this is the popular matching that matches it to P2. What about A4? P4, P2, right? So somebody does this, we have done this by examining this instance, but suppose there is an algorithm that does this, what we observe is that this must belong to this belongs to AF, because, yeah. A3 gets matched to, sorry, A3 gets matched to, yeah, go ahead. Okay, so okay, so I think this is P3, right? I'm sorry, yeah. Okay, good. Thank you for pointing out. Yeah. So therefore this is P3, and so therefore what we see is this applicant is in the set AF, because every popular matching matches it to its F post. This applicant is in the set AS. These two applicants are in the set AFS, just to say that they can get sometimes matched to F, sometimes matched to S. But my question was that will it happen that there are 4 posts underlined in that the algorithm that underlines posts will have 4 posts underlined? Yeah. There can be multiple stable partners, right, for an an A in the stable marriage setting. You have seen in yesterday's tutorial that there were 4 stable matchings and there can be multiple stable partners. Similarly, can the underlining algorithm have 4 different pos? Yes, no. No, why? Okay. Yes. Because if it is a popular matching, it better match it to either its FA or SA, that is the characterization. So one, if there has to be an underline, it be on your rank 1. One of them has to be for your rank 1. It may not be there, like it did not happen. And then there is one more where somewhere down the line, but there is only one more. So there are only two popular partners that you can have. One which is your F post if it is, the second which is your non-F post if again it is, because maybe it is the case that there is no other post that you get matched to. There are only 2 different ranks that an applicant can get matched to in different popular matchings. There may be multiple popular matchings, but you either get it to your F post or you get it to your S post. So now how do you identify these, or what algorithm allows you to underline these is something that we will study via a tool which is a very nice and useful tool which is called as the switching graph. So I'll go back to the example. So how do you copy? This one is it? Uh, okay. And I just do this. Thank you. Edit and then? Yeah, thank you. Yeah, thank you. Yeah, so we will draw this, we will say what the switching graph is for yeah. So we will say what this switching graph is, and it's a very nice tool. So this switching graph is a graph which is constructed only on the posts. So we will have the vertices as our posts in the original instance. So in this we'll show this by an example. So it is, we will have P2, P1, P2, P3 and P4. So is there anything else? P1, P2, P3, P4, yeah. That's all. So we will have the vertices as the posts of the original graph, and this switching graph, because of the name, it says it is going to switch, allow us to switch from one popular matching to another popular matching. So it is always constructed with respect to some popular matching of the instance, right? So our popular matching algorithm has already given us one popular matching. We have assumed that the instance admits a popular matching. So it has given us one popular matching. So what is one popular matching? I will use that, I will use some circling to do that. So just one second. So I will remove this underline now. Because we remember what it is. Yeah. So one popular matching is this red matching, which is P1, P4, P3 and P2, and there is another green matching which has P2, P3, but then these are same. right? This is how the switching graph, sorry, this is the how the two popular matchings look like. So let's construct it with respect to one popular matching, which is the red popular matching, right? So for every matching, let's call the red matching, you have M of A, right? So because it's a popular matching, every applicant is matched. So we have M of A for an applicant, we have M of A, and remember M of A should come from F of A or S of A, because that is how the popular matching matches it. So there is always another post which we'll call other of the matching, other than the matched post, right? So O M of A, and we cannot know, we don't want to commit whether M of A is F of A or the other post is S of A, so we'll just call it the other post, right? We don't know whether it is F or S, so we'll call it the other post with respect to that matching, right? So now what we will do is we will draw edges which correspond to the applicants of the original instance. So the vertices of this graph are the posts of the original instance. The edges of this graph will be applicants of the original instance. So currently A1 is matched to P1. What is its OM of A? Because A1 is matched to P1, its OM of A is S of A. What is S of A? P2. So I will draw an edge from P1 to P2 and call it this agent A1, right? Because this is corresponding to that. Now we can do this for everybody. What about A2? What is OM of, what is M of A actually? P4. And what is OM of A2? P1, right? So we will go from P4 to P1. This edge is labeled as A2, right? What about A3? It has its red matched partner as P3 and its OM is P2, right? So P3 to P2. What about A4? So this is A3 and this is like this, A4. Is this fine? So this is how I will construct the graph. So I'll repeat, vertices is equal to posts of G, edges is equal to applicants, and Pi to Pj, this is a directed edge, okay? This is a directed edge from Pi to Pj if M of Ai is equal to Pi, that is Ai is matched to Pi and OM of Ai is equal to Pj. That is its other post that it could have gotten matched to in a popular matching is Pj. This is the way the graph is defined. Is there any difficulty about the way the graph is defined? Okay. So let's ask, how complicated can this graph look like? How difficult or how complicated is this graph? When I draw this graph on a big instance for an instance of a popular matchings with some popular matching M. So the switching graph is always constructed for a popular matching M, which is given to us. So somebody has constructed that. So let's talk about outgoing edges from a vertex. How many outgoing edges can a vertex have in this graph? So the question is number of outgoing edges for any, so remember the vertices are posts for any post Pi. Yeah, so you had some answer? Is that how we drew the outgoing edges? So let's read, when do we draw an outgoing edge from Pi to Pj? When Pi is the matched partner of Ai and Ai thinks that Pj is its other partner, right? It has nothing to do with F pose. But you are correct in another flip direction. I'll come back to you. So you had some answer? Yeah. So louder. No, so I am not asking for P1. For any P, how many outgoing edges can be there? P1 it is actually, yeah, so in this example, how many outgoing edges does every vertex have? 1. Can it have more than one outgoing edge? Okay, so how will it have more than one outgoing edges? So when will it have? Hmm. Okay, another applicant has that as a first post. But when do you draw an outgoing edge from a vertex? So, okay, so where are you talking about these outgoing edges? So it is in this switching graph, okay? Yeah, okay. So we are not talking about the reduced graph, the graph and so on. So those are undirected graphs. So we are talking about the switching graph. Okay, so I will repeat, I take a vertex, I will draw an outgoing edge from that vertex. So I will call that post Pi. If Pi is matched to Ai in that matching M and the matched partner Ai of that post thinks that Pj is its other OM of that Ai, right? So now how many matched partners can Pi have? How many matched partners can it have by the definition of a matching? Just one, right? So I'll be able to draw only one outgoing edge from a post. But now what you are thinking about is how many incoming edges does it have? So how many incoming edges does a vertex have? As many as the number of applicants who treat that post as OM of that with respect to the current matching. It doesn't have to be first post because we don't know. But of course, it either is a first post or an S post because a post cannot simultaneously be treated as an F as well as S, right? So therefore, every post has just one outgoing edge, but a post can have multiple incoming edges, right? This graph can have, in this example we don't have, actually we do have multiple incoming edges for P2, right? So we can have multiple incoming edges, but we cannot have multiple outgoing edges. We have exactly one outgoing edge, not exactly one. So can a vertex not have any outgoing edge? Sorry? Yeah, anybody? Okay, so yes or no, it cannot have any outgoing edge. You can have a vertex which does not have any outgoing edge. Okay, why, when will it happen? Okay, remember that we haven't identified whether it is AF or AS yet. In this example, we have eyeballed and identified, but remember that if an agent is matched to somebody, it is either it's F or S and it always has the other thing, right? So remember the vertex is corresponding to a post in this in the original instance. So when will a vertex not have an outgoing edge? Yeah, so when will a vertex not have an outgoing? Mhm. Good. So if a vertex or a post is not matched to any applicant, then we cannot draw an outgoing edge from it, right? Because we say that you look at that vertex, you draw an outgoing edge from that vertex if it is matched to some applicant and that applicant treats Pj as its other post. But if that vertex is unmatched, if that post remains unmatched, then you cannot draw an outgoing edge from it. So a simple example of this is, so if you have A1, A2, P1, P2, sorry P1, P1, P3, P4, right? So then you will have a popular matching which is A1, P1, A2, P4, and the switching graph will have the switching graph will have P1, P3, P4. So now if you are drawing the switching graph with respect to this, you will ask, is this post P1 matched and what is its other thing? It is actually P3, and what is the other thing, which is this thing? So it will have an outgoing edge to P3, P4 will have an outgoing edge to P1 because this is corresponding to A2, this is corresponding to A1, but P3 cannot have an outgoing edge because there is no applicant which is matched to it, and therefore there is no OM of that applicant, right? So unmatched posts will not have an outgoing edge, right? So in this graph, the unmatched post will not have an outgoing edge. So I will repeat this, that every post has at most one outgoing edge, and if a post does not have an outgoing edge, it is unmatched in M. So one last question and we will stop here. We have not done the cheating strategies, we will do it tomorrow in the first class. But if a post is unmatched, what can you say a little more about that post? Remember, it is about popular matchings. So there is something that we know about the post. They are of two types. What do you know about that post? It is an S post. It cannot be an F post because all F posts are matched. So if a vertex does not have an outgoing edge, then it must be an S post, right? So and such a post is an S post. Yeah. So I think I'll stop here and I'll have to continue tomorrow in my first class. Yeah. Okay.